So our next speaker over here will be Qing Long Fu, and he'll be talking about the ion uptake kinetics in bloom-forming cyanobacteria. Okay.
Good morning, good afternoon, everybody. My name is Qing Long Fu. I'm from Tokyo Institute of Technology. I'm a postdoctor in the water environment laboratory. Today, my presentation is about the ion uptake kinetics of bloom-forming cyanobacteria. My presentation can be divided into 5 parts, and the first part I would like. And the first part, I would like to briefly introduce my master study using the cyanobacteria, and then I will talk about the ion uptake by molecular system. And firstly, let me see the cyanobacteria reactor. This is my master study. We have constructed a bioreactor using a clarifying cyanobacteria, using we choose the Nostog this strain. This is the this is my reactor, and this is a cyanobacteria. As you see in this picture, cation was effectively removed by over 98%, and in most deaths, the cation concentration in the effluent water is lower than the limits of the drinking water of China. We also investigated the cadmium species in the cell. We found that most cadmium is accumulated by cyanobacterial cells because cellular cadmium, it is the most organic bond cadmium is predominant cadmium species in the cell, and also we found a very low concentration, low contents of carbonate bonded cadmium. The presence of this carbonate bond cadmium suggests that some cadmium was bonded on the surface, was bonded to calcium carbonate precipitation. And based on the SEM EDX, we confirmed that there is cadmium bearing calcium carbonate precipitation. Why cadmium was incorporated or absorbed by on the surface of calcium carbonate precipitation on the cell surface? Because in the calcium-rich microenvironment, cyanobacteria can induce the carbonate precipitation occurs when the products of calcium and carbonate concentration exist the Kp value of calcium carbonate precipitation. Due to the similar analytical lattice of cadmium and calcium, cadmium is expected to incorporate into the lattices of the calcium carbonate precipitation, and then they will be stably immobilized in the neutral to organic environments. All this finding provide a new insight into the understanding of the removal mechanism of cadmium from the calcium-rich water using cyanobacteria. And then I would talk about the ion uptake by molecular system. As we know, iron is a very important and instant nutrient for the growth of cyanobacteria. It as a cofactor of metal images and proteins. Iron is very important to many metallic processes. In the Earth's crust, iron is the second most abundant metal. However, in most natural fresh waters, the concentration of dissolved iron is limited, and even sometimes under the eutrophic conditions. Therefore, iron is a main factor limiting the growth and primarily productive of phytoplanktons, and it is closely linked to the water quality, supply, and treatments. Because of the low solubility of inorganic ion. Organic complex ferrolic is the dominant ion species in the water system and also can be considered as the ion pore in the water. Generally speaking, only uncharted ferric and uncharted ferrules are available to most microbes. So, as the ion pore in the water, organic complex ion can be transformed by uptake or biotic pathways to form the inorganic ferric or inorganic ferrules, and then finally uptaked by cyanobacteria. Right now, there are many studies using the artificially prepared media to investigate how ion was uptaked by the microsystem. And they found that inorganic ferric is the main species. However, compared to the artificially prepared media, in the environment real waters, it is highly complex. For example, the natural organic matter is unpredictable, and also the anthropological impact can impact the water qualities largely. So, in the environment real waters, how microsystem cells uptake ion from inorganic ferric or inorganic ferrules, it is not clear. So let's go to similar results. In my study, we have collected 41 samples. 41 samples from Sagami River water, Sagami River best, and there are three types of water: river, reservoir, and the effluent water from wastewater treatments. And for these types of water, we detected high concentrations of nutrients, including iron. Why we choose microsystem to study? Because this cyanobacteria can grow very fast, and it is global distribution. And also, some toxins of this cyanobacteria, some strands of this bacteria are toxic to many microbes, and also to humans. Let's see this elimination experiment. We found that compared to the dark conditions, and the light condition, ion uptake decreased by about 30 to 40 degree, 30% degree. And also, we added a very strong ion charge, fluorine, because the complex of ion and fluorine is not bioavailable. So in this experiment, we added fluorine to capture the photo-generated inorganic ferrules. As you see in this picture, we found that the photochemically generated inorganic ferrules contributes mainly to moderately to the overall cellular ion uptake. And then in the next step, we improve the visual miracle, this software to calculate the inorganic ferric concentrations in the Sagami waters based on the water parameters. Once we get this inorganic ferric concentration, we improve those concentration into the ion uptake kinetic models. Based on the parameters, on the uptake parameters of inorganic ferric that published in EST from our lab, and the visual militate delivered inorganic ferric concentrations, we found ion uptake rates can be reasonably modeled by the Michel-Merton model. So our results in the section 2 and section 3 indicates that inorganic ferric is a major ion species that are available to the microsystem. And also, based on the bioavailable statistic analysis, like PCA and Poisson's collection analysis, we found that this is ion uptake lattice. Ion uptake lattice, it is positively related to DLC and many nutrient concentrations. For example, iron, zinc, and manganic cobalt, and but relatively connected to the DL and pH. Those results suggest that ion uptake by microsystem in the Sakami water is related to the water variables and also affected by the ethnopagenic inputs. In the next step, based on the multiple linear regression, we constructed or built this uptake model. We found that our built uptake model can reasonably predict ion uptakes in the Sakami waters. This is 9 to 1. We see in most cases point is around this 9 to 1. But you see, for the ethnopagenic water, the standard value is larger, so it means that ethnopagenic inputs affect ion uptake largely. And then this is my conclusion. And the Cyanobacteria reactor water is supported by NSFC and CIS, and my current ion uptake work is supported by the Japan Society of the Promotion of Science. Okay. Thank you.
All right, thank you very much, Qing Long. We have plenty of time for questions, but could I just ask everyone to wait for the microphone, please, before asking the questions so that we can record the question and answer session. Are there any questions, please? Okay, I will start. So you use Michaelis-Menten kinetics to model your ion uptake,
Yes.
which works very well if you know that iron is the limiting nutrient. But given that it's a micronutrient and there could be other metals that are limiting growth, could you just comment on whether you're sure that iron is the limiting nutrient in your situation?
No, iron is not the only. Iron is not the only limited factor, limited nutrient because this is a natural water. It's natural water, liver water, natural liver and reservoir and water. So. In most cases, we have detected the concentration of many metals, and we see because in different regions, the range is very large. Sometimes other metals also limited the growth of iron, and also, but sometimes it is not, and as well as iron.
Any last chance for questions? All right. Thank you, Qing Long.
Thank you.